Welcome to The Explainer. Right now, we're tracking an absolutely massive cosmic event that's unfolding as we speak and rolling right through May 17th. We are talking about intense solar winds crossing literally millions of miles of deep space to deliver the ultimate weekend forecast, a spectacular Northern Lights show. Let's get right into it.
Seriously, stop scrolling for just a second. If you're glued to a screen right now, you might actually want to start making plans to look up at the real sky this weekend. Over parts of the US, the night is about to suddenly light up with one of the absolute most breathtaking natural shows on planet Earth, the Aurora Borealis. The urgency here is very real, but you know what the most incredible part is? The sheer, mind-boggling scale of what's causing this. This magnificent display actually starts 93 million miles away. We're talking about massive, roaring waves of energy ejected straight from the sun, hurtling through the vacuum of space at over 1 million miles per hour, just to paint our weekend sky.
Okay, let's dive into this. What we are dealing with this weekend is specifically classified as a G1 geomagnetic storm. Now, if you're already tracking space weather with us, you know that as we ramp up toward the solar maximum of solar cycle 25, these kinds of disturbances in Earth's magnetosphere are popping up way more frequently. But a G1 is super notable right now because of the dense, ultra-fast stream of solar wind that's acting as the trigger. Scientists are glued to the telemetry of this stream, and for good reason. When a dense pocket of that solar material slams into our magnetosphere, it essentially squishes or compresses our magnetic field. That sets off the exact atmospheric cocktail needed to push the northern lights much further south into parts of North America than they usually set.
According to NOAA's Space Weather Prediction Center, this entire phenomenon plays out in 3 incredibly violent yet beautiful phases. It all kicks off when a fast solar wind erupts, basically escaping through a massive coronal hole in the sun's atmosphere. Because the magnetic field lines in these holes are open, the plasma isn't held back at all. It just blasts right out into the solar system like a cosmic fire hose. Then, those charged particles cross the interplanetary void, devouring that 93 million mile gap in just a matter of days. Finally, when these high-energy particles actually arrive here, they slam into our planet's magnetic field. They get funneled down toward the magnetic poles, where they violently collide with atmospheric gases to produce those iconic glowing waves we all want to see.
And man, when that high-speed collision happens, it produces highly specific glowing waves of color. But hey, these aren't just random pretty shades. They're actually a direct chemical signature of our atmosphere. It's like a giant neon sign. The stunning shades of green we usually see, those are caused by charged particles colliding with oxygen molecules roughly 60 to 190 miles above the Earth's surface. The vibrant reds, those happen when that exact same oxygen is struck much higher up, like above 200 miles. And those deep, beautiful purples, that is the distinct signature of nitrogen being ionized. The Aurora Borealis is quite literally a giant floating chemical heat map of solar energy colliding with Earth's atmospheric layers.
So the science is obviously spectacular, but it all comes down to one really practical question for us. Are you actually in the drop zone for this weekend's show? We know what's happening and the exact atmospheric chemistry behind it all, but the real trick is knowing if your geographic location aligns with the shifting magnetic latitudes of this specific geomagnetic storm. Right now, the data pinpoints prime viewing regions across northern states like Alaska, North Dakota, Minnesota, Wisconsin, Michigan, and Maine. What's really fascinating about this specific footprint is how the magnetic latitudes actually shift during a G1 event. Normally, the auroral oval sits way up close to the pole, but as this G1 storm compresses the Earth's magnetic field, that oval expands southward. Suddenly, states like Maine and Michigan become absolute prime real estate. Their geomagnetic latitude drops right into the active zone, assuming, of course, the storm's KP index, which is our primary measure of geomagnetic disruption, hits at least a 5 or higher. If you're in these areas, you are perfectly positioned.
Now, keep in mind, the window for this is incredibly tight. The initial impact of the solar wind hits on May 15th, and that kicks off the geomagnetic disruption. We then get a sustained period of ongoing activity rolling right through May 16th before the primary stream of charged particles passes and the storm window officially slams shut on May 17th. So this isn't some week-long celestial event you can casually catch later. It is a rapid multi-day window where the Earth is directly sweeping through the heaviest concentration of this solar material. Time is definitely of the essence here.
Within that super brief multi-day window, NOAA's Space Weather Prediction Center has actually narrowed down the absolute optimal viewing time. We're looking at between 11 p.m. and 2 a.m. Eastern Daylight Time. And there is a very specific, really cool scientific reason for this exact time frame. It has to do with a concept called magnetic midnight. Basically, this is the point during the night when your specific location on Earth is aligned directly opposite to the sun, placing you in the best possible position right under the auroral oval. If you want the highest chances to catch those greens, reds, and purples, setting your alarm for this specific 3-hour window totally maximizes your alignment with the planet's magnetic tail.
So the crucial point is, viewing is never guaranteed. I know, it's a bit of a bummer. But as structured, predictable, and perfectly measurable as this G1 storm is on our scientific instruments, nature remains, well, entirely unpredictable. Even if you are in the perfect geographic location, at the exact perfect moment of magnetic midnight, there are dynamic, highly localized variables that remain entirely out of our hands.
Honestly, space weather enthusiasts already know that forecasting the aurora is really only half the battle. The reality down here on the ground dictates what you actually get to see. Local weather and cloud cover, that's the obvious barrier. But beyond just finding dark skies away from city light pollution, you are totally at the mercy of real-time magnetometer fluctuations. Even right in the middle of a G1 storm, the interplanetary magnetic field, specifically a metric called the B's component, needs to tilt southward. If that magnetic orientation randomly points north instead, well, the solar wind simply bounces right off our magnetosphere like a giant shield, and the show stops cold, regardless of how perfectly dark or beautifully clear your sky is. All of these macro and micro conditions have to align just right.
But listen, if you are lucky enough to be in the viewing regions this weekend and the data aligns, do yourself a favor and step outside. You just might witness one of nature's absolute most magical displays. If you're tracking the storm, definitely drop a comment and let us know where you'll be watching from. We can map the solar winds and track the magnetic waves all we want, but as our source materials so perfectly reminds us, the universe always has another surprise waiting. And honestly, it really makes you wonder, what exactly is brewing on the far side of the sun right now, just waiting to head our way? Keep your eyes on the skies, everybody, and stay curious.